Quantum mechanics is a branch of physics that deals with the behavior of matter and energy on the smallest scales, such as individual atoms and subatomic particles. It is a fundamental theory that has been extremely successful in describing the behavior of the microscopic world and has led to a wide range of practical applications, from quantum computers to medical imaging. However, quantum mechanics is very different from classical physics, which describes the behavior of the macroscopic world we see around us. Hello viewer, welcome back to another video. In this video, we will examine the key differences between quantum mechanics and classical physics. Superposition. In classical physics, a particle can be in only one state at a time. For example, a ball can be either at rest or in motion, but not both at the same time. However, in quantum, particles can exist in multiple states simultaneously, a phenomenon known as superposition. This means that a particle can be in multiple locations or have multiple energies at the same time. This concept is the foundation of quantum computing, where multiple states can be used to store and process information. Uncertainty. In classical physics, the position and momentum of a particle can be known with complete certainty. However, in quantum mechanics, the Heisenberg uncertainty principle states that the more precisely the position of a particle is known, the less precisely its momentum can be known, and vice versa. This means that there is an inherent uncertainty in the behavior of quantum particles. This principle has been experimentally verified numerous times and is considered one of the cornerstones of quantum mechanics. Wave-particle duality. In classical physics, particles are treated as discrete objects, while waves are treated as continuous. In quantum mechanics, particles exhibit both wave-like and particle-like behavior. This duality means that a particle can exhibit wave-like behavior, such as diffraction and interference, as well as particle-like behavior, such as quantization of energy. This is a central concept in quantum mechanics and has been experimentally verified numerous times. Non-deterministic nature. In classical physics, the motion of a particle is determined by the laws of motion and can be predicted with certainty. However, in quantum mechanics, the outcome of a measurement cannot be predicted with certainty. This means that the behavior of quantum particles is inherently non-deterministic. This concept is often referred to as the principle of wave function collapse, where the wave function of a quantum system collapses upon measurement, abruptly changing the state of the system from a superposition of states to a single definite state. Quantization of energy and angular momentum. In classical physics, energy and angular momentum can take on any value. In quantum mechanics, however, energy and angular momentum can only take on specific discrete values. This means that, for example, an atom can only exist in certain energy levels, and not any value in between. This concept is the basis of spectroscopy, where the absorption or emission of light is used to study the energy levels of atoms and molecules. Entanglement. In classical physics, particles are treated as separate entities that do not interact with each other. However, in quantum mechanics, particles can become entangled, meaning that the state of one particle is correlated with the form of another, even if they are separated by a significant distance. This non-local behavior has been experimentally verified and is considered one of the most intriguing and mysterious aspects of quantum mechanics. Probabilistic interpretation. In classical physics, the motion of a particle is determined by the laws of motion and can be predicted with certainty. In quantum, however, the results of a measurement are described by probabilities, rather than definite values. This means that, for example, the probability of finding a particle in a certain location, rather than a definite position. This probabilistic interpretation of quantum mechanics is a major departure from the deterministic nature of classical physics and is one of the key differences between the two theories. Complex wave function. In classical physics, waves are described by a real-valued function, such as a sine or cosine wave. In quantum mechanics, however, the wave function is complex and includes both magnitude and phase information. This complex wave function is used to describe the behavior of quantum particles and is one of the central mathematical tools of quantum mechanics. The collapse of the wave function. In quantum mechanics, the wave function of a quantum system collapses upon measurement, meaning that the system state abruptly changes from a superposition of states to a single definite state. This collapse of the wave function is considered one of the most fundamental aspects of quantum mechanics and is responsible for the probabilistic nature of quantum measurements. It is also the basis for the idea of quantum computing, where the collapse of the wave function is used to perform computations. Non-local behavior. One of quantum mechanics' most intriguing and mysterious aspects is its non-local behavior. This means that a particle can instantaneously affect another particle, even if they are separated by a large distance. This non-local behavior is a fundamental aspect of quantum mechanics and is one of the key differences between quantum mechanics and classical physics. In summary, quantum is a fascinating and powerful theory that has changed the way we understand the behavior of matter and energy on the smallest scales. The differences between quantum mechanics and classical physics are numerous and profound, ranging from the superposition of states to the probabilistic interpretation of measurements. These differences are responsible for the unique and sometimes mysterious behavior of quantum particles and have led to a wide range of practical applications, from quantum computing to medical imaging. Despite its success, however, quantum mechanics remains one of the most mysterious and challenging areas of physics, and there is still much to be understood about the behavior of quantum particles. Please follow us on social Facebook, Instagram, LinkedIn, Twitter, Tumblr, and Reddit, with links in the description. And don't forget to subscribe to our YouTube channel. See you soon.